Hey everybody, it's Dr. D. Hope you're well. I want to talk today about hypothesis testing for two means when sigma 1 and sigma 2 are known. Right, so we're going to maintain the assumption. We're kind of going back to one of the terrible assumptions, the assumption that we know that our population standard deviations, just because it lets us use our z-statistics and makes the math a little bit simpler. We don't have to worry about more complicated arithmetic just yet. We're just trying to get some of these concepts down. So we're going to take a look at a practice problem that gives us kind of some insight into what this can be useful for. If you remember last time, I talked about the intuition and how we have obvious differences, right, between two populations that allow us to discern for any given element whether it belongs to population 1 or population 2. And that makes that differentiation quite cheap. What we want to know is, can we learn something more subtle and maybe more valuable, but that would be expensive to find out. And if we can find some relationship there, then we can identify by looking at it, say, oh, this is population 1, that means it's more likely to be this. This is population 2, it's more likely to be this. So let's take a look. On problem set 5 here, we've got during the 2013 season, Major League Baseball took steps to speed up the play of baseball games in order to maintain fan interest. The average duration of a game from a sample of 60 games played during the summer of 2012 was 2 hours and 52 minutes. The average duration of a game from a sample of 50 games played during the summer of 2013 was 2 hours and 46 minutes. For the purposes of this question, let 2013 games be population 1. So they're telling us that we're going to call population 1 games played in 2013, and population 2 games played in 2012. And it might seem a little counterintuitive, but often because of the way the math's going to end up, often we do after minus before, and that's kind of what we're going to be looking at, because that lets us think intuitively. It makes the intuitive, or the intuition is the word, I guess, the noun version there, a little more straightforward, right, of changes, right? When things change, usually we take after minus before to look at that change. And so how is this going to work? Well, we're going to be doing a hypothesis test. Let's read 1A. A research hypothesis was that the steps taken during the 2013 season would reduce the population mean duration of baseball games. Formulate null and alternative hypotheses. So we want to test, did games get shorter, essentially, is what they said they wanted to take steps to speed up the play. And then you can see the rest of the questions. They want a point estimate of the reduction. This part asks for a p-value and a conclusion. And then they want to know about a percentage reduction in the mean duration of games, baseball games here. Or it should be 2013, not 2003. And then they want to know, should they be pleased? Discuss. So essentially, they want us to run a hypothesis test and then answer some questions about it. So we're going to go through the 5 steps to try to figure out whether games got shorter, and then we're going to try to learn from that. So step 1, as has been the case in the past, is to state our hypotheses, right? To formulate our hypotheses. Now, these are a little bit trickier because if we want to say, for example, they want us to see if we can prove, right? Research hypothesis usually means alternative, because that's the thing we're trying to see. Do we have data enough to show this? So that means it's going to be the alternative. And so the alternative is going to be essentially that games got shorter. But that's not. We want to state it in terms of a parameter that we can learn something about. Last time we learned about the distribution of the difference between two sample means. So what we're going to try to do is we want to convert this into a test of the difference between two population means. We want to convert it to a test of mu1 minus mu2. So we've got to work our way to a mu1 minus mu2. And generally speaking, when you're doing problems like this, the form these are going to take when we're done looks like this. mu1 minus mu2. And then there's going to be some sign, and then there's going to be some value we're going to call d0, and then mu1 minus mu2, and then the opposite sign, and then some number, call it d0. And then up here, just like we have in the past, you could have a greater than or equal to sign, or a less than or equal to sign, or an equal to sign. And then down here, you'd have the corresponding binary relation, a less than sign, or a greater than sign, or a not equal to sign. This right here, that d0 stands for the difference under the null, and it's almost always going to be 0. but it doesn't have to be. It turns out that the math that we're using for this would hold just as well if that were non-zero. So for example, let's say they wanted to test, did it reduce games by 10 minutes? Then that D0 could be 10. We just want to know if they got shorter. So let's take a look at how we would describe mathematically games got shorter. Remember, mu1 is the average length of a 2013 game, and mu2 is the average length of a 2012 game. And so if games got shorter, what that would say is, if you took a game, mu1, right, that's 2013, and then you compared it to mu2, which would be a 2012 game. If games got shorter, then mu1 should have fewer minutes than mu2, right? mu1 is going to be smaller than mu2. Right? That's the alternative that they're trying to show. We're trying to prove here. And so that's a question: did games get shorter? And if we want to convert this into a test of a difference between mu1 and mu2, what we can do is we can just subtract mu2 from both sides. If we subtract mu2 from both sides, what we'll find is that this kicks out a hypothesis that meets our criteria. mu1 minus mu2 is less than 0, and that has the corresponding null, h0. mu1 minus mu2 is greater than or equal to 0. So since 2013 is population 1, it's useful to go back and think through this, right? So our null is that we're going to assume that if you took the number of minutes in a game in 2013 and you subtracted the number of minutes in a game in 2012, you would either get the same number, 0 out, or you'd still have more in 2013, which is another way of saying that games got longer. There would be minutes left over. If that turns out to be false, then we will have conclusively shown that if you take the number of minutes in a game in 2013 and subtract the number of minutes in the game in 2012, you will run out of minutes because these games have fewer minutes, and having fewer minutes is another name for a game being shorter. And that's what we want to test. Did games get shorter? So that is the end of step 1. And then when I put these in, let's see, does this work? H0. There we go. And then HA. There. mu1 minus mu2, and then this should be greater than or equal to, should be less than, I can just type a less than sign, and then this should be 0, this should be 0. All right, I think, okay, let's see, I think I accidentally hit less than wrong. And there we go. Okay, so that should be mu1, mu2 is less than 0 is where we find, right? 2013 after minus before gives us less than 0. All right, now this one's the point estimate. We're going to find that on the way, but I want to stick with our 5 steps. The next step is to choose alpha. And so I'm going to scroll down and see here. Here it says 0.05 is the level of significance. And so there we go. We want to find that level of significance. And it should be, that's it, or I'm sorry, that is it. We have found the level of significance. Next is step 3, which is to choose a test statistic. Step 3 is to choose a test statistic. And so what we're going to do is we're going to look at the standardized normal distribution thing we looked at in the previous video. We're going to modify it slightly to give us our test statistic for this case. So what we came up with last time when we talked was a score formula that looked like this. Our sample statistic is the difference, the sample mean difference between those two, minus mu1 minus mu2 divided by square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Now this would be great. This would be a score formula if we knew this, right here, or if we knew either of these. But we don't. That's the whole point of a hypothesis test, is we're trying to infer what this difference might be or whether it meets our assertion at the very beginning. So we're going to replace this with D0, and that will give us our test statistic. So our test for two means sigma's known looks like this. Z equals x bar 1 minus x bar 2 minus d0. Again, that 0 means it comes from the null, divided by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And under the null, this has a standard normal distribution. It's normal 1, 0 if h0 is true. And if you recall from the previous sets we've worked on, this tells us what to do in step 4, and this tells us what to draw, what formulas to use in step 5. So for step 4, we're going to compute the value of this test statistic. In order to do that, I'm going to jump down here to 1c. We're going to need, we've got sample 1 and sample 2, and then we're going to need x bars for 1 and 2. We're going to need sigma, and then sigma squared, and then n for 1 and 2. And if we look up, we can see x bar 1 is the sample mean. In 2013, which is population 1, it was 2 hours and 46 minutes. So I'm going to do 2 times 60 plus 46 because I want to measure how many minutes it was, right? That's my goal is to measure it in a constant unit. Minutes is the easiest one to deal with here. In 2012, it was 2 hours and 52 minutes. So I'll do the same or very similar formula: 2 times 60 plus 52, and that's my formula to find the difference in, or the minutes for population 2. Sigma, here it says, historical data indicate a population standard deviation of 12 minutes is a reasonable assumption for both years. Conduct the hypothesis test and report the p-value. At a 0.05 level of significance, what is your conclusion? So if sigma is 12 for both of these, sigma squared is going to be 144, right? I can raise it to the second power. For n, I have to go back to the original question to find these. 2013, it looks like we had 50 games. 2012, we had 60 games, right? That's where those came from. So 2013 is 50 games. Right? This is population 1, which is 2013. Population 2, which is 2012. This is 60 games. And then I'm going to have to calculate my sigma squared divided by n. Just so you can see that formula again, what I'm doing here is I'm just dividing that by n. And now I'm running out of space a little bit. You should have more space because you don't have all these explanations. But what I need to do is I need to combine those together. That's going to be the variance, right? So if I add sigma 1 squared over n1 plus sigma 2 squared over n2, that'll be my variance. Actually, let me move this out of the way because I really don't need these right now. I'm going to need x bar 1 minus x bar 2. So that's x bar 1 minus x bar 2. And then my variance is sigma 1 squared over n1 plus sigma 2 squared over n2. Got this formula here. This formula here. And if I wanted to write this out at this point, I could. That'll give us a nice way to slow it down a little because we're a little in the weeds. What I would have is z equals -6 minus d0 over the square root of 5.28. And so I need my d0. Well, my d0 is just taken from my null in the alternative. So that's just this number right here. That's a 0. And so my z numerator is going to be x bar 1 minus x bar 2 minus 0. My z denominator is just the square root of the variance right here. And that gives me all the stuff I need to calculate my z-stat. My z-statistic is going to be my z numerator divided by my z denominator. And that is the end of step 4, right? If you calculate this all out, you end up with z equals -2.61. Now I want to pause for a second there just to think about what just happened. What we did was we took 2 samples, we subtracted their means, and then we calculated the variance of that distribution. And then we used that to calculate a z-statistic. What this essentially says is, if the null is true, what we witnessed, the combination of these 2 samples and this difference between them, is the same as drawing a sample that has 2.61 standard deviations to the left of the mean. Is that reasonable or not? Well, that's what step 5 is for, is to figure out what's the likelihood of that. So let's take a look at step 5. Just as always, with step 5, we're going to find a p-value and then draw a conclusion. And we learned from step 3 that the distribution we're drawing from is a standard normal. So we've got a standard normal curve here with a mean of 0, standard deviation of 1. And then our test statistic is over here at negative 2.61. We have to look at the alternative hypothesis to figure out whether it's a left tail test or right tail test. Here you can see there's a less than sign, and that's how we know that is a left tail test, right? Because it's an arrow that points to the left. So that's where that comes from. So we're going to have a left tail test, which means that the p-value is going to be the size of this area here. It also means that we don't have to manipulate it at all, because Excel has a left tail formula built right in, right? Norm.s.dist, and then we put negative 2.61, comma 1 for cumulative, and that will give us our left tail, which is our p-value in this case. So right in this p-value area, I can do norm.s.dist, and then put my z-stat, comma 1. And there you go, that's correct. Now, to decide whether to reject or fail to reject the null, we need to remember the rejection rule. The rejection rule says that if your p-value is less than alpha, you reject the null. Otherwise, you fail to reject the null. So our p-value is 0.0045. Our alpha, we said, was 0.05. And our p-value is indeed less than that. So we are going to reject the null. All right, that's correct. Okay, let's look back at the rest of the question to try to figure out what this means and what the answer to some of these other questions are. Here it wants the point estimate of the reduction in the mean duration of games. I think it's 6. It's the difference between our two samples, right? So right here, there we go, negative 6 is correct. What that's saying is that, we reduced the time, the length of time that it would take to play a baseball game by 6 minutes, right? That's what that point estimate is meaning. And that's our estimate. Our point estimate is if you had to pick a number, what would it be? It was a 6-minute reduction. What was the percentage reduction in the mean duration of baseball games? Well, usually we divide by before. Let's see if I coded this right. So our reduction is 6, right? So reduction 6. And then our before length was 172. So our percent reduction should be percent reduction negative 6 divided by 172. Let's convert that to a percentage by clicking the little percent button there. I could use a few more decimals in here. There you go, 3.5%. Let's see if this gives it to us. Incorrect. I wonder if it wants it to be positive. Yeah, that's 3.5% reduction. So it should probably be coded as the absolute value. With reductions, it's always a little bit careful because negative 3.5% increase is really what we're saying, which is a 3.5% reduction. I wonder if this one also gives it to you if you put 6 here. It does, but then this throws this one off. Okay. So this one just checks for absolute value, but this one, we have a 3.5% reduction. Finally, should management be pleased with the results of this statistical analysis discuss? Not really is what I would say. I mean, maybe. Think about this for a second, okay? So you put a wide-ranging set of rule changes into play to try to reduce the mean duration of games. And as a result, we showed that you statistically significantly reduced them, right? There was enough of a reduction that it was not just noise. There was a true bona fide reduction. That said, you only reduced it by 6 minutes. I don't know. I guess raise your hand if you heard that a baseball game took 2 hours and 52 minutes and you were still interested in seeing it. Raise your hand. Okay, now let's say that you heard it took 2 hours and 46 minutes and would you be interested in seeing it? Raise your hand. Like, who's changing their mind there, right? Who's on that margin? I think, again, this is unrelated to statistics, but related to baseball and marketing, I guess. I think it's useful to know that, like, baseball is by its very nature a slow game, right? Part of what happens is you build tension, and then that tension is released, and there's a lot of time where nothing's happening. But that's part of the appeal of baseball, right? It's an excuse to sit outside on a nice day and just have a conversation and eat a hot dog or Dippin' Dots and just watch something happen while you spend some time. But it is a pastime, right? The purpose is the passage of time. Maybe, as a result of that, You get 6 more minutes that you could devote to commercials, I guess, so maybe they should be happy about that. I really don't think, I think trying to make baseball fast and exciting is probably barking up the wrong tree. Anyway, the real takeaway though is that we can tell the difference between these two sets of games because one of them took place one year, one of them took place another year, and then we also can tell because of our statistical analysis that one set of them is shorter, and that takes more measurement. It's not right there in the name. Hope you found this useful. We relied on the presence of our population standard deviations this time. Next time, we're going to get rid of those. We're going to use our sample standard deviations instead. And just like we've seen in the past, the result of that will be that we are no longer using our Z statistic. We're going to have to come up with a T statistic. So that's where we'll go next. I will see you guys next time. If you have any questions, as always, please get in touch. I'm always happy to help. Bye, guys.